Hi everybody. Um, Today what I'm going to talk is going to be about the lab EL21A. It's the time domain the simulation of electric circuits. That's for a sophomore student in electronics engineering EL. Before we go to the circuit, actually it's just like simple circuit. It's the RLC circuit in series or arrangement, and we're going to analyze the circuit by looking at actually I have the circuit just right here. Okay, so this is only RLC circuit in series arrangement, and you have our input signal as the pulse. Before we go through over there, you have to record for the voltage drop across capacitor and also the voltage drop across the resistor, as well as the current flowing through the circuit. So let's get there. Start with the recall about what you know or about basic knowledge about our resistor, capacitor, and our inductors. For the first one is for resistor. You have that the resistance in the unit of ohms, that's the independent of frequencies. But for capacitors and inductors, of course, this is they are depend on frequencies. For capacitor, you know that the impedance, which is in the unit of ohms, right? That's the vary with frequency. The higher frequency you have, the lower impedance you will be. But for inductors, the impedance also depends on frequencies. The higher the frequency you have also higher impedance. Okay, and now what else about our resistor? You can see that the voltage drop across resistor is going to follow Ohm's law, V equal to IR. For capacitor, let's take a look this one quick. And the impedance of capacitor is will follow the equation 1 over j omega c, and omega equal to 2 pi f, where f is the frequency, right? And for the inductor, the impedance is going to be j omega L. So that's why when the frequency increasing, you have the impedance also increasing too, right? Now take a look at the voltage drop across resistor. By Ohm's law, V equal to IR. That's very simple. For capacitor, you know that the current flowing through the capacitor is going to be equal to C dVc by dt. So whenever you have the voltage across the capacitor change, according to the time, that's will have the current capacitor. Now for the inductors, you know that you can find the voltage drop across inductors, V equal to L dIL by dt, right? So whenever you have the current flowing through inductors, vary with time, that will create the voltage drop across the capacitor. That's the basic knowledge that you already know about it. Okay, now take a look at the start from RC circuit in series arrangement. I'm going to derive some expressions according to the circuits by applying KVL, Kirchhoff voltage law. You know that Vs, the supply voltage or the input voltage, is going to be equal to the voltage drop across resistor plus the voltage drop across capacitor. So you can write Vs in the term of equal to VR plus Vc. Now you are looking for the voltage drop across capacitor, so you rearrange the equation You have Vc equal to Vs minus Vr, and then your Vc going to be you simply take a look at Vr. Vs is constant because it's the pulse. If the amplitude is equal to 1, what I have here is just that you will supply the input pulse when the time passes by 1 milliseconds, and the pulse we will go to the setup for pulse, and I explain that to you later on. Now VR, that's going to be equal to our IC. You know, the same IR or IC is the same because this is in a series arrangement. And then you have IC equal to C dVc by dt. And you're looking for Vc, right? You need to rearrange equations. So you're starting by do some integration. So from this equation, what I did here, I divided by Vs on the left of equation, divide Vs minus Vc divided by Rc. That's equal to that's equal to dVc by dt. And then you move Vs minus Vc to the right, and you move dt to the left, and you're ready to do the integration. So on the left, you integrate with respect by dt. So start from the limit of integration, and start from 0, the time of 0, and then the time of t. It's on the right here, dVc divided by Vs minus Vct. You integrate with respect to Vc, and start from V at t equal to 0 and V at arbitrary time. So on the left you have Ln over Vs minus Vc. Okay, you start from here. Actually, I switch around. So I take a Vc minus Vs, so you have the negative side here. So that means you put the limit of integration start from V0. So that's why I have Vc at t equal to 0 right here, and then minus Ln over Vs minus Vc at any time. And on the right is simply this is 1 over Rc is constant, so you end up with the t, and then you take the limit from 0 to t, so you end up with the t over Rc. Now you can find our Vc, right? So this one you have the exponential of you're going to have this one Ln minus this one, so simply Ln over both term are divided. You have a Vs minus Vc divided by Vs minus Vc, and then you can find Vct. So this term simply become Vs minus Vct divided by Vs minus Vc at the time of 0. And on the right, of course, you have exponential to the power of negative t over Rc. And you know that your Rc is simply a time constant. To see how fast the capacitor will be charged or discharged, really. And then you end up with the Vc. So you can work this out by yourself. It's just like simple math. And finally, you have our Vc over time that you're looking for. It's going to be equal to Vs, which is the input voltage, plus Vc at the time of 0 minus Vs, and then the whole thing multiplied by exponential over the power negative t over Rc. And then if at the time of t0 you have no voltage across capacitor, so that means Vc at the time of t equal to 0 is going to be equal to 0. So this term Vc 0 is drop out. We have Vc equal to Vs minus Vs exponential negative t over Rc, and then you take the common term out, Vs So you end up with VCT equal to Vs multiplied by 1 minus exponential negative t over RC. Well, if you analyze the equation, you can see that for the time equal to 0, this term become 1, right? So you have 1 minus 1 become 1. So VCT equal to Vs multiplied by 0. That means equal to 0. So at the time t equal to 0, when you switch the input signal or the supply voltage, you don't have a voltage across the capacitor. Now when the time passed by, this term dropped, right? Because this term becomes smaller and smaller. So finally you're going to end up with VCT equal to Vs, and that's we call a fully short of your capacitor. Now you look for the voltage drop across resistor. From the KVL, you have Vs equal to VR, voltage drop across resistor plus voltage drop across capacitor, and then you rearrange the equation to find VR, or voltage drop across resistor. That's going to be equal to Vs minus Vc, and you already have Vc. You derive the equation for Vc before, which is this term. So you substitute Vc this is your Vc, right? So you substitute Vc in the equation. You have VR equal to Vs minus Vct, and this is your Vct. And then Vs cancel out, right? This is minus and minus, so you end up with Vs, the last term, multiplied by exponential to the power of negative t over RC. And now for the current flowing through the circuit in the series arrangement, you have IR equal to IC. You look for IC, right? IR, you follow Ohm's law, V equal to AR, so it ends up with VR divided by R, and your VR you already derive here. VR, voltage drop across resistor, is equal to Vs multiplied by exponential to the power negative t over RC. Okay, so you have three of them. You have the current flowing through the circuit, you have the voltage drop across resistor, and also you have the voltage drop across capacitor, all of this. Now let's get started with the AltiSpice. Okay, you go to File, you go to our new schematics. This one I'm going to do only RC circuit in series arrangement. So sorry, let's start with R. You control R to rotate, left click to place, and right click to stop. Next one, you need a capacitor, right click to stop, placing the capacitor. Also you need ground key, and then you look for the input signal. I'm going to pick up what? The voltage, right? Click OK. Left click place, right click to stop. And now you do the circuit again. So I'm going to move components. Okay, that should work fine. And now you go to wiring, right? You click this one, and then you make connection of the components. So R to capacitor, capacitor to ground, and your ground connected to the input signal, right? And now you change the value of your resistor. So I make the right click on the R and change the value, and that one requires to be your 10k ohms. And for C, I'll look for this one to be your 0.1 microfarad. 0.1 U. Okay. And for the input signal, we're going to apply pulse. So you make a right click on this the voltage, and you go to advanced, and you go to pulse. Okay, we're going to need the pulse have the amplitude of 1, so the initial to be 0 and V on to be 1. The time delay, that means when the time you will switch to turn on the switch to supply the input voltage. I'll put this one as 1 millisecond, 10 milliseconds, sorry about it. It doesn't matter, you can set up any value you want to put it in. For T-rise, for the pulse, the spice not allow you to make the rise time to be 0. It's not allowed, so you just just put any small number. So I'm put like 1 nanoseconds. And T4 also 1 nanosecond. Oops, 1 nanosecond. T on, you don't care about it. T period. Actually, if you want that's the pulse train, you can put the period or the pulse width. But this one, when we turn on, is simply you apply 1 volt, supply voltage, to the rest of your time. So, I'm done with this. I'll click OK. Well, that's why you have the information about the input voltage to be pulse. 0 is mean, start from 0, and then you have to amplitude to be 1, and the switch on is 10 milliseconds. And the rise time and the fall time is 1 nanosecond. 1 nanosecond is the same. Okay. Now, the next one, you go to setup, because you want to see the plot of the voltage drop across capacitor, the voltage drop across resistor, and also the current flowing through the circuit. So you go to edit, and you go to PSpice analysis, and you want to work on the time domain, right? So you go to the transient. Let's take a look at your stop time. You can keep, the plots go on and on, but let's see if you don't put any number in here, what's gonna happen. But we're going to work on, the transient. Stop time. Let's see. Okay, you can try this one by yourself. If I click OK, what's gonna happen? Oh, that's one missing stop time. Let's put this one to be 10 milliseconds. Okay. You click OK, and you place the command box into the circuit. Let's change this one, the pulse. The switch on 10 milliseconds is too long, so let's put this one to be only 1 millisecond. Alright, click OK. And to be easy to find your voltage drop across C, so let's put the label text in here. You simply move your cursor around on the line, and you make a right click and label net. Let's put this one to be like we see, the voltage drop across capacitor, and you locate your label text box on the line. Make sure that you have the yellow line here. So that means this one is going to be the reference as the VC, or the voltage drop across capacitor. So you make a left click, you place this one, and right click to stop. Okay, now you're ready to do the simulation. So let's go to a simulation, or you just simply use icon the guy running here. So now they're doing the simulating. Okay, so you have the plot, and what you're looking for is what you add trace, right? This icon, just like the mountain here, pick visible trace. So you look for the voltage drop across capacitor. So you have the voltage drop across the capacitor. You take a look at this one. When the switch on, before the switch on, the voltage drop across capacitor is 0, right? And when the time pass by, when you switch on, you have a supply voltage, so the capacitor start charging, and then finally it's going to reach, you know, the voltage of 1 volt as the input voltage, 1 volt. That's very clear, right? And you also will be able to add trace, right? Plus setting, you go to add trace. You want to also look for the voltage drop across resistor. Now you have problem because the voltage drop across resistor is going to be what? It doesn't show VR1. Let's try this one again. I'm missing something. Address. What is this one? VN001. That seems to be the input signal, right? When you turn on the switch, you have the voltage as the pulse, not the pulse trend. Or simply you have the supply voltage is 1 volt, you know, all the time. Now, how do you find the voltage drop across resistor then? It's going to be some problem here. Let me break this one a little bit. Okay, I forgot. Okay, that's actually is very simple. So the voltage drop across resistor is going to be the voltage, you know, V1 minus Vc. Okay, so you go to the plot. I already have this one, so let's start over again. So let's go back to address the voltage drop across capacitor, right? The green line, and the blue line is the that's the input voltage. And now you go to plot setting again, you go to address, and now you want to find the voltage drop across resistor. So that means you have a VC, voltage drop across capacitor, minus the input voltage, or V at the node N001. So you click OK, and then you're going to have the red line. Seems to be something wrong. Try it again. Plot setting, address. So VNO1 minus the voltage drop across the capacitor VC. So this is the red one. This means the voltage drop across the resistor. Now you take a look at the equation that we derive. This is your VR, right, equal to Vs exponential negative T over RC. At the time equal to 0, you can see this obviously, you know, VR equal to Vs, right, because exponential to the power of 0, that's equal to 1. So at the start, you know, at t equal to 1 millisecond, you have the voltage across resistor to be 1. And then by following the expression here, Vs multiplied by exponential negative t over RC, when the time increased, this term are getting smaller, right? So that's mean you have Vs multiplied by a smaller term. So finally it dropped, because when the time go to you know, very large, this one dropped to be 0. So exactly follow the expression of your voltage across resistor. Okay. Now if you take a look at the you want to find the voltage or the RC. Let's see. You have to do some math a little bit. Okay, from your RC or your time constant is going to be what? Let's close this one. Okay. Alright, let's blow this up a little bit so you can see better. Right. So your R is what? 10K, right? Then I'm gonna put 10E3. That means 10K. 10 multiplied by 10 to the power third, 10 to the cube. And then your C, you have 0.1 microfarad, right? So that's 0.1 negative 6, or to the power 10 to the power negative 6. That's your C. And now your time constant is going to be what? Equal to RC, right? So multiply this R by C. So this is your time constant in the unit of second. So that's look like 1 millisecond, right? 1.0 multiplied by 10 to the power negative 3. Okay, that's your time constant. So what I'm looking for here, just compare. If you want to look for the time constant from the plot, you know that your VC equal to Vs minus 1 over exponential negative t over Rc. You talk about the time constant, that means your voltage drop down to the power of exponential negative 1. So put this one exp negative 1. So that's mean it dropped to 0.67 times of your maximum voltage. So let's say your voltage is like 1 volt, right? So I put this one as the part of this one. So you look for what? 1 minus 0.367 ignite. So let's approximate. So you have 0.632. 0.632. That means this one have to drop, somewhere 0.632. The way you look for, you're going to look for the time constant. We are focusing on the green line, right? We see. So what you can do, you can put cursor. Actually, you can put just right here. You see the cursor, and you notice here on the bottom left, you have coordinate x and y, right? Coordinate x is mean the time, and y is simply the voltage. So you look for y equal to 632. 632, and you can see, oops, it's a little bit difficult here. 632. Okay, let's make 0.63. You have the time is about 2 milliseconds, which is the become the time constant. Let's see what's wrong here. You have this one to be what? The time constant is 1 millisecond, right? But why we have like 2 milliseconds? R equal to 10K. That's correct. C equal to 0.1 microfarad. So you have time constant 1 millisecond. You just go to the plot when the voltage reach about 0.63. I don't have, I probably do something wrong just at this point. 0.62, 0.62. Well, I got 2 milliseconds. Oh, I see. Because you switch on at 1 millisecond. Sorry about that. So you have at 2 milliseconds. That means it take about 1 millisecond, to reach the voltage of 0.63. Okay, of 1 volt. So it's exactly the same as from the calculation. The time constant equal to R multiplied by C. Okay, hopefully it's not make you confused. Just follow that again. Okay, so that's one how to analyze the circuit. Look for the voltage drop across capacitor and the voltage drop across the resistor or the red line. And you also look for the current flowing through the circuitry. So let's see how it look like. By follow the equation, the current is equal to Vs multiplied by exponential negative t over RC divided by R. So the current seem to be at t equal to 0 is supposed to equal to Vs over R, or 1 over what, 10k, right? What is 1 over 10k? It's going to be 1 multiplied by 10 to the power negative 4th, right? 10k divided 10k. R is equal to 10k. Vs equal to 1. So that's equal to Vs divided by R. Your R is what? 10k, 10e to the power 3. So that's your current in the unit of amp, or simply 0.1 milliamp, right? Let's see. You can get the same from the plot. You go to plot setting, you go to address, and you go for any of them. IC equal to IR equal to IV1. So I just click on IR1. Where is that one? IR1. Let's cue this, guys, so you can see better. Here. So I1, when the time passes by, it's the you have this one 100 microamp. Actually, it's become 0.1 milliamp, right? Just like you have here at the start at t equal to 0. Okay. And then after that it's starting dropping down when the time passes by. Finally your current is going to be equal to 0. That's all about how to analyze your circuit using LT Spice 4. And then the rest you want to continue, or you go to the part 2 of your lab. Now you have to do RLC circuit in series arrangement. So you add another inductors into the circuit. You can work this out. Okay. And this one is going to more complicated because you are talking about a second order circuits, because you have a device that depend on frequency. Here this means you have L and C, right? The frequency dependent. And then you need to analyze, overdamp, critical damp, and underdamp. You can do the circuit by LT Spice. Okay, so let's stop just right here, and then we can continue, analyze the circuit later on. This is your circuit. Okay, I'll see you in the next video. Okay, bye.